Assalamualaikum warahmatullahi wabarakatuh, Doctor. So our presentation will start with the abstract. This project designed a smart thermal fan that automatically adjusts its speed based on ambient temperature. It also includes a real-time temperature display and a sound control mode for hands-free activation. The system uses an NTC thermistor to detect temperature and control the fan motor, a voltage sensing circuit for the display, and a sound sensor to react the acoustic signals like clapping. In conclusion, this fan demonstrate how fundamental physics principles can be applied to create an energy-efficient, user-friendly, and intelligent home appliance. As we move on to the introduction, energy efficiency has become a major concern in modern households as electricity consumption continues to rise due to the increasing use of cooling appliances such as fans and air conditioners. Conventional electric fans operate at fixed speed and require manual adjustment, which often result in unnecessary energy usage. Smart home technologies are gaining popularity because they allow devices to automatically adapt to their surroundings, improve convenience, and reduce energy waste. In line with this trend, the development of automated fan system has become an important area of interest. Most existing models focus solely on temperature-based control, but many lack additional features that improve user interaction, such as real-time temperature feedback or hand-free activation. This highlights a gap in current low-cost educational prototypes that integrate multiple smart functions while remaining simple enough to construct and understand using basic physics principles. Our team has discussed a few problem statements, which is the first one is traditional household fans cannot adjust their speed automatically based on changes in room temperature. 2. Traditional household fans do not provide real-time temperature information to users. And the last one is they rely entirely on manual switching, making them less user-friendly for children, elderly individuals, or users with limited mobility.
So now let us go through the objective of this project, which is to design and construct a smart thermal fan to automatically adjust its speed according to the ambient temperature. Next, it is to integrate a temperature display module to provide a real-time temperature readings. Moreover, it is to implement a sound control mode that allows the fan to be activated or deactivated through sound cues such as clapping. This project aims to also apply physics concepts such as a heat transfer, thermistor resistance, Ohm's law, and acoustic signal detection to develop an efficient and user-friendly device. Finally, it is to demonstrate how basic physics principles can be used to create innovative and energy-efficient smart home technology.
So now I'll be explaining about the methodology of this project. There are several materials used in this project. For example, the DC motor, which provides the rotational motion needed to spin the fan blades, the plastic fan blades to convert the motor's rotation into airflow, allowing the fan to function, the negative temperature coefficient NTC thermistor to sense the temperature changes, sound sensor module to detect clapping or sound signals to activate the fan through the sound control, LCD or digital temperature display module to show the current temperature measured from the thermistor in real time. The transistor acts as a switch or amplifier to control the motor based on signals from the thermistor or sound sensors. The resistors limit the current, protect the components, and form voltage dividers for accurate sensor readings. The breadboard and jumper wires provide a platform to assemble the circuit without soldering and allow easy connections between components. The 9-volt battery and connector supplies electrical power to the entire circuit. The multimeter, which is to measure the voltage, the current, and resistance for testing and troubleshooting the circuit. The smartphone tachometer application is also used to measure the fan's rotational speed, or also known as RPM, using the phone's camera. And lastly, we have the hairdryer as a heat source. It provides controlled heat to test how the thermistor responds to the increasing temperature. Now I'll be explaining about the procedure to do this project. So firstly, the DC motor with fan blades was mounted securely on a stable base. An NTC thermistor and a resistor were connected in series to form a voltage divider, which was linked to the transistor's base to control the motor current. The motor, transistor and power source were connected to form the temperature-controlled speed circuit. The LCD temperature display module was connected to the sensing circuit and set to convert the thermistor voltage into temperature readings. The sound sensor module was added to the control circuit so that a clap or short sound triggered a signal to switch the fan on or off. All components were assembled on a breadboard and the connection was checked with a multimeter to ensure proper voltage and current flow. The model was tested at different temperatures by warming the thermistor with a hairdryer, and the fan speed, display readings, and sound control response were recorded. For the next part, I will be explaining about the data analysis. The temperature readings were taken from the LCD, and fan speed was measured using a smartphone tachometer. A table and graph of fan speed versus temperature were created. The thermistor voltage was also measured to see how temperature affected its resistance. The sound control feature was tested by checking how often the fan responded to claps. All data was organized and analyzed using simple averages, trends, and comparisons.
In this project, our group is discussing two aspects of design. Firstly, is the thermistor. For this part of the project, we focus on how the NTC thermistor reacts to changes in temperature. The NTC thermistor has a special property. When the temperature increases, its resistance decreases. Because of this lower resistance, more current can flow to the motor. As expected result, the fan spins faster at higher temperatures, where resistance continues to drop while the fan speed decreases. The LCD readings also show the temperature measured through the thermistor voltage conversion. These readings match the actual ambient temperature, which confirms that the sensor is functioning correctly. In this part, which is the sound-based system, for the sound system-based control system, we tested how accurately the sound sensor responds to claps. The sensor is designed to detect short and sharp sound pulses. In our trials, most claps were detected successfully. However, a few misactivation happened due to inconsistent clapping or slight background noise. Despite this, the overall activation accuracy remains high, around 90 to 95%. This shows that the sound activating control system works reliably for hands-free operation.
The Smart Energy Saving Fan successfully demonstrates how temperature can control motor speed using simple electronic components. This project integrates concepts from heat, electricity, and mechanics, proving that physics can be used to design cost-effective and sustainable technologies. This model encourages innovative thinking towards smart home systems that save energy and contribute to a greener environment. We would like to express our sincerest gratitude to all of these individuals for mentoring and supporting us in completing this project. We would like to thank Dr. Umar bin Abdul Halim, our physics lecturer, for providing us with invaluable insights and direction. To University Putra Malaysia for the guidance, materials and opportunity given to participate in the Apex mini project. To our parents, their constant encouragement, patience and understanding have been the pillars for our project. We are grateful to our colleagues who contributed ideas and perspectives that enrich this project. Thank you everyone for shaping this project and enhancing our learning experience.